Okay, here's the next step in the evolution of these problems. This one's going to be having a lot more steps, and it's going to be a little bit more difficult to get to the point we got to on the other ones. But again, the steps are going to be the same, so we're just going to be looking for the resistance total, and once we find that, we're going to find our voltage and current totals and then work backwards through that. Now, every time after we get those values and you work backwards, you're going to have to ask yourself, for whichever resistor you're looking at, which rules apply to it based on is it in series or in parallel with the other resistors that it's in reference to. So step one is going to be combining R2 and R3. We're going to add them because they're in series with each other. So 3.3 plus 8.2, that gives us 11.5 kilo ohms. So we take our reciprocal value formula for the parallel resistors. We'll find that 11.5 kilo ohms and 4.7 kilo ohms. Comes to a total of 3.336 kilo ohms. Now this value is a combination of everything on this end of the circuit here. So in reference to that one, R1 and R5 are in series with this value. So that means that we can just add those together. Now we'll pay attention to our units again here because we have kilo ohms over here. So we're going to take 3,336 ohms plus 330 ohms plus 10,000 ohms, and that's going to give us a grand total of 13,666 ohms. So if we divide 9 volts by that resistance total that we have for right here, let's see what we get there. So we get 658.569 microamps. Again, we can't plug either of these values in straight across because we have a combination circuit here. So what we're going to have to do is break them down backwards. So resistor 1, the total of resistor 2, 3, and 4, and resistor 5 are in series. So based on those being in series, they're going to all get the same current. So resistor 1, we can carry this value across, because since it's in series, it's going to have the same total. So this one's going to have 658.569 microamps, and resistor 5 is going to have the same because that one is also in series with that value. So over here we're going to have 658.569. Now we'll be able to multiply that by 10,000 to find the voltage drop right there. So if we take 10,000 and multiply it by 658.569 microamps, that's going to give us 6.586 volts. 6.586 volts. And then if we take the 330 and we multiply that by the 658.569 microamps, see what we get there. That gives us 0.217 volts. All right, now we know that this other resistor here, that's a combination of the others, we know that that's going to have the same current. Because this value is in series. So if we multiply that by the resistance value, so we're going to multiply this by this, we get 2.197 volts. Now that 2.197 is going to go down both branches here. So knowing that's going down both branches, since R4 is by itself and is not in series with anything, we know that that's going to be the same voltage as the one going down that branch. So R4 is going to be 2.197 volts. Now the 2.197 going down this way towards R2 and R3 is going to have 2 voltage drops across these resistors. So we can't write that value in there. What we're going to have to do is do some other math to find out what the current is and then divide those. But first, let's go back to R4. So we got enough information over here to solve for the current. So let's fill in that one first. So if we got 2.197 volts, we divide that by 4,700 ohms, we're going to get 467.447 microamps. Okay, over here. So if we get our voltage that's going down this direction, we know if we add these two together, we have this value right here. So to find the current for this combined value, which is this entire branch here, we can take the 2.197 and divide that by this number here, 11.5 kilo ohms. So 2.197 divided by 11,500 gives us a current right here of this combined value of 191.043 microamps. So since these are in series with each other, we know that the current's going to be the same. So this 191 can go over both resistors. So R2 and R3 are going to have 191.043 microamps. 191.043 microamps. Now we can just use the two values and solve for the voltage drops across those two. So let's do that. So 0.000191.043 times 8,200 ohms gives us 1.567 volts. And then we'll do the other one. So now we got 0.000191.043 times 3,300 gives us 0.630 volts. Alright, it looks painful at first, but it's going to get easier. So just keep practicing. And again, just ask yourself what values or what rules you're using. You know, are we talking about this total resistance value here for this entire leg? Well, then that means we're in series. And then if we're looking at these individual values here, then we're looking at being in parallel. It takes some getting used to, but it's going to be easy. It's just repetition. All right, let me know if you need any more.